Solving homogeneous differential equations via substitution. Now, before we dive into the new material, let's take a moment to reflect on what we have already covered. In our previous lessons, we focused on solving differential equations where the variables were already separable, meaning we could easily move all the x terms to one side and all the y terms to the other to integrate them. However, as we move into more complex mathematics, you will find that many first-order differential equations are not immediately separable. They often appear tangled up in a way that prevents that simple separation. But here is the good news. There is a specific class of equations known as homogeneous differential equations that we can tackle. The key insight we are abouting today is that by using a strategic substitution, we can actually transform these complex, non-separable equations into a much simpler variable-separable form that we already know how to solve. Welcome, everyone. Let's begin our new lesson on solving homogeneous differential equations via substitution. In the next few slides, I will show you exactly how to identify these equations and the step-by-step process for performing that transformation. Goal of the method. To make these equations solvable, our objective is to perform a change of variables. We are going to transform the dependent variable from y into a brand new variable, which we will call v. We define this new variable v as the ratio of y over x. Now that we understand that some equations aren't immediately separable, let's look at our primary goal for this method. By making this substitution, we aim to simplify the structure of the equation so that we can eventually use the separation of variables technique we studied previously. Step-by-step conceptual framework. Now that we understand the core idea, that we want to transform a difficult equation into a simpler, separable one, let's look at the actual framework you'll use to solve these. To solve a homogeneous differential equation that is written in the form di by dx equals f of x and y, you are going to follow a specific 5-step process. The very first step is the substitution. Since we know these equations depend on the ratio of our variables, we are going to introduce a brand new variable, which we'll call v. We define this such that y equals v times x. If you look at that algebraically, it also implies that v equals y divided by x. Your goal in this first step is to take your original equation and rewrite it entirely in terms of this new ratio, replacing the y terms with our new v and x terms. This sets the stage for the next step, where we'll deal with the derivative. Step-by-step conceptual framework continued. Now that we have established our substitution in step 1, where we let y equals v times x, we need to move on to step 2, which is differentiating the substitution. Remember, our goal is to replace every instance of y and its derivative in the original equation. Since we are introducing a new variable, v, we can't just leave the derivative as di over dx. We need to find an expression for di over dx in terms of our new variable, v, and our original variable, x. To do this, we look at our substitution, y equals v times x, and treat it as a product of two functions, v and x. This means we must apply the product rule. Let's walk through the derivation. We start with the derivative of y with respect to x according to the product rule. The derivative is equal to the first term, v, multiplied by the derivative of the second term, which is the derivative of x with respect to x, plus the second term, x, multiplied by the derivative of the first term, which is the derivative of v with respect to x. Now we simplify. The derivative of x with respect to x is simply 1. So, our equation becomes v times 1 plus x times dv over dx. Finally, multiplying v by 1 doesn't change it, so we arrive at our essential formula. Di over dx equals v plus x times dv over dx. Keep this formula in mind, because in the next slide, we are going to plug both our substitution and this new derivative back into the original differential equation to transform it. Step-by-step conceptual framework continued. Now that we have established our new expression for the derivative in the previous slide, let's move on to step 3, which is the transformation of the equation. At this stage, you are going to take everything we have prepared and plug it back into your original problem. Specifically, you will substitute both y equals v times x and replace the derivative, di dx, with our new expression, which is v plus x times the derivative of v with respect to x. Once you perform this substitution, you'll notice something very important. The resulting equation should now only contain the variables v and x. Now, you might be wondering, why does this happen? Well, because we started with an equation that is homogeneous. The x terms on the right-hand side will mathematically cancel each other out. This is the magic of the method. It leaves you with a function that is solely in terms of v. This is crucial because, as we will see in the next slide, this transformation is exactly what allows us to move into the separation of variables. Step-by-step conceptual framework, continued. Now that we have successfully transformed our original equation into a new form using our substitution, we move on to step 4, which is the separation of variables and integration. As you saw in the previous slide, the substitution process has stripped away the complexity, and the equation is now in a variable separable form. This means we can now use the standard techniques we learned earlier in the course. First, your goal is to rearrange the equation. Move all terms involving the variable v, along with its differential, dv, to one side of the equals sign, and move all terms involving x, along with its differential, dx, to the opposite side. Once you have successfully separated the variables, the second part of this step is to integrate both sides of the equation. Finally, and this is a crucial step that we will see applied in the upcoming example, do not forget to add the constant of integration, c, to your result. This constant is essential for representing the general solution to the differential equation. Step-by-step conceptual framework, continued. Now that we have successfully integrated both sides and found our solution, we reach the final, crucial step in our framework. Step 5, back substitution. At this point in the process, you'll notice that the solution you've just calculated is expressed in terms of the new variable, v, and the original variable, x. However, remember that our original problem was posed using y and x. To make our answer meaningful and complete, we cannot leave it in terms of v. Therefore, you must go back through your equation and replace every single instance of v with the ratio of y over x. This step allows us to return to our original variables and find the solution in terms of the original variables, y and x, just as the problem originally requested. Illustrative example. Now that we have walked through the theoretical framework and the step-by-step process, let's put everything we've learned into practice with an illustrative example. Here is our problem. We need to solve the differential equation where di by dx equals the quantity x squared plus y squared, all over 2xy. To begin our step-by-step solution, the very first thing we must do is perform identification. Before we jump into any substitutions, we have to verify if this equation is actually suitable for the method we just discussed. We need to check if the equation is homogeneous. To do this, we look at our function, f of x and y, which is x squared plus y squared over 2xy. Notice that in the numerator, the sum of the powers in each term is 2, and in the denominator, the sum of the powers, x to the first and y to the first, is also 2. Because the total degree is the same for every term, we can confirm that this is a homogeneous function of degree 0. This is our green light to proceed with the substitution method we'll see in the next few slides. Illustrative example, continued. Now that we have identified our equation as homogeneous, let's move into the actual execution of the method. First, we perform the substitution. As we discussed in our conceptual framework earlier, we are going to introduce a new variable. V will let y equal v times x because we are changing the dependent variable. We must also update our derivative. Using the product rule, which we just covered in the previous slides, we replace the derivative of y with respect to x with the expression v plus x times the derivative of v with respect to x. Next, we move to step 3, transforming the equation. This is where the algebra happens. We are going to take our original equation, which was the derivative of y with respect to x equals the quantity x squared plus y squared, all over 2xy, and plug in our new terms. On the left side, we replace the derivative with our new expression, v plus x times the derivative of v with this x. On the right side, everywhere we see a y, we replace it with v times x. This gives us the numerator as x squared plus the quantity v times x, all squared. In the denominator, we replace the y with v times x, giving us 2x times v times x. If you look closely at the denominator, you'll see we have two x's being multiplied, which simplifies to 2vx squared. Now, if we expand that squared term in the numerator, we get x squared plus v squared times x squared. We are now in a much better position to simplify the equation, which is exactly what we will see on the next slide. Illustrative example, continued. Now let's pick up where we left off on the previous slide. We have our equation expressed in terms of v and x, but it still looks a bit cluttered with those x squared terms. First, we are going to factor out x squared from both the numerator and the denominator. As you can see, the x squared in the top cancels out with the x squared in the bottom. This leaves us with a much cleaner expression. V plus x, di by dx, equals 1 plus v squared, all over 2v. Notice how the x terms have vanished from the right-hand side. This is exactly what we hoped for when we identified this as a homogeneous equation back in step 1. Now that we've simplified the expression, we move into step 4, which is separating the variables. Our goal here is to get all the v terms on one side and all the x terms on the other. To start, let's isolate the term containing di by dx. We'll do this by subtracting v from both sides of the equation. To combine these, we need a common denominator. So we rewrite v as 2v over 2v. This gives us x, di by dx, equals 1 plus v squared minus 2v squared, all over 2v. When we simplify the numerator, 1 minus v squared, we get x, di by dx, equals 1 minus v squared, all over 2v. Finally, we perform the actual separation. We'll multiply both sides by 2v and divide by the term 1 minus v squared, while moving the dx to the right side. This leaves us with the fraction 2v over 1 minus v squared, multiplied by dv on the left, and 1 over x, multiplied by dx on the right. We have successfully transformed a complex equation into a separable form, which sets us up perfectly for the integration step you'll see on the next slide. Illustrative example, continued. Now that we have successfully separated our variables in the previous step, we move on to step 5, integration. We are looking at the integral of 2v over 1 minus v squared with respect to v, which equals the integral of 1 over x with respect to x. To solve the integral on the left side, we'll use a simple u substitution. Let's set u equal to 1 minus v squared. If we differentiate that, we find that the derivative of u is negative 2v times dv. This allows us to transform the left side into the negative natural log of the absolute value of 1 minus v squared. On the right side, the integral of 1 over x is simply the natural log of the absolute value of x, plus our constant of integration, c. Now, to clean this up, I'll move the negative sign from the left side to the right side, making it plus the natural log of the absolute value of 1 minus v squared equals negative c. Using our logarithmic properties, we can combine those two logs on the left into a single natural log of the quantity x times 1 minus v squared. To get rid of the natural log entirely, we can exponentiate both sides. This gives us x times 1 minus v squared equals k, where k is just a new constant representing e to the power of negative c. Finally, we reach step 6, back substitution. Remember, our goal is to express the solution in terms of our original variables, x and y. So, we must replace every instance of v with y over x. When we plug that in, we get x times the quantity 1 minus the fraction y squared over x squared. If we distribute that x into the parentheses, the first term becomes x, and the second term becomes y squared over x. To clear the fraction, we multiply the entire equation by x, which leaves us with x squared minus y squared equals k times x. And there we have it. This is the general solution for our differential equation. Real-world context, scale invariance. Now that we have mastered the algebraic steps of solving these equations, let's take a moment to step back and look at why this mathematical technique actually matters in the real world. You might be wondering, why do we care about equations that can be simplified by looking at ratios? The answer lies in a concept called scale invariance. When we say a system exhibits scale invariance, we mean that the fundamental behavior of the system doesn't change just because you change the scale or the size of the objects involved. This is exactly what we saw in our substitution step, where we replace the absolute values of y and x with the ratio v equals y over x. In the fields of physics and engineering, a homogeneous differential equation is used to describe systems where the rate of change depends specifically on the ratio between variables, rather than their absolute magnitudes. To make this concrete, let's look at an example from fluid dynamics. Imagine water flowing through a pipe or air moving over a wing. The behavior of that flow often doesn't depend on the absolute distance from the edge of the pipe, but rather on the ratio of your distance from the boundary to the total width of the pipe. Because this relationship stays consistent regardless of whether the pipe is 1 centimeter wide or 1 meter wide, we use these homogeneous equations to model it accurately. Common mistakes to avoid. First, there is the risk of forgetting the product rule. When we perform our substitution, it is tempting to simply replace the derivative of y with respect to x with the derivative of v with respect to x. However, as we practiced in slide 4, because we defined y as v times x, you must apply the product rule. This means you must always substitute the derivative of y with respect to x as v plus x times the derivative of v with an x. If you skip this, the entire transformation fails. Second, keep a close eye on algebraic errors during simplification. When you substitute y equals v times x into your equation, your goal is to reach a state where the x terms cancel out. You must ensure you are factoring x out of every term completely. A helpful tip: if you find that x is still lingering in your equation and hasn't canceled out, stop and recheck your work. It is a strong signal that the equation might not be homogeneous or that an algebraic error has occurred. Third, do not neglect back substitution. This is a very common mistake where students perform the integration perfectly, but then stop the problem right there. Remember, our original problem was written in terms of y and x. If your final answer contains the variable v, you haven't finished the job. You must go back and replace every instance of v with the ratio of y over x to return to our original variables. Finally, be extremely careful with sign errors during integration. As we saw in our illustrative example, when integrating terms like 2v over 1 minus v squared, the sign is critical. Remember that the derivative of the denominator, 1 minus v squared, is negative 2v, not positive 2v. A small slip with a negative sign here will lead to an incorrect logarithmic expression and an incorrect final solution. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. As we've seen through our step-by-step framework and the worked example, this method involves several moving parts, and it is very easy to trip up on the details. Let's look at 4 specific mistakes you should watch out for. Keep these points in mind, and you will find much more success with these types of differential equations. Key takeaways. All right, we have reached the end of our lesson. Let's take a moment to recap the key takeaways from today's session to ensure you have a solid grasp of the material. First, let's remember the primary purpose of this method. We use substitution specifically to transform a non-separable homogeneous equation into a separable one, which allows us to use the integration techniques we've already mastered. Second, you must memorize the core substitution. Remember, we define y equals v times x, and when you differentiate that, you must apply the product rule, which gives us di over dx equals v plus x times dv over dx. This is the engine that drives the whole process. Third, keep this 5-step workflow in mind as a roadmap for every problem. First, substitute. Second, simplify the algebra. Third, separate the variables. Fourth, integrate both sides. And finally, always remember to back substitute to return to our original variables. Lastly, how do you know when to use this method? You can verify if an equation is suitable for this technique if the right-hand side can be rewritten entirely as a function of y over x. If you can see that ratio, you are ready to proceed with the substitution. I hope this summary helps solidify your understanding. Keep practicing these steps, and you'll find that these complex-looking equations become much more manageable.